Okay, we were looking for amplifiers and we want to design a op-amp, but when I started looking op-amp design, I figured out that we haven't done frequency response, and one of the features of an op-amp design is the bandwidth calculations for a given what we called as phase margins. So I thought that I should quickly first run into frequency response of amplifiers, and we will also give you a simpler method of calculating dominant and non-dominant poles. Okay. So today maybe or even tomorrow, I do not know how much, we will just look into frequency response. All of you are aware that a transfer function like AVS can be given as DC gain AV0. This is S by WZ, this is not clear, plus 1 divided by S by W1 plus 1, S by W2 1. WZ stands for the 0 of this transfer function. Essentially it means at that frequency the transfer function has a value 0, whereas W1 and W2 are called poles, which essentially means at those frequencies the gain becomes infinite, okay, or unstable as such. So in a typical MOS amplifier we have around, typical of course, it is not necessarily 2 only, but normal amplifiers will have 2 poles, sometimes 3 poles, and if you have a diff amp plus driver plus buffer plus output amplifiers, it may have more than 3 poles as well, and more than 1 zeros also. But normally for a simple amplifier which we will discuss first, there will be 2 poles and a 0 in most likely event. Okay. The most passive circuits which we use as filters, like a low pass filter and a high pass filter, an RC network has one capacitance and therefore one time constant and therefore one pole. Okay. These are called single pole transfer functions. So we will first look into quickly those single pole transfer functions. These are all standard, you are done in second year, nothing great has been told. All that I am saying, the in a transfer function denominator gives poles, numerator gives you zeros, as can be seen from the function itself, and AV0 is called DC gain. I repeatedly tell you earlier also that DC does not essentially means DC, okay. Though please take it from me, an op-amp is also a DC amplifier. Is that clear to you? A op-amp is also a DC amplifier. So even at 0 frequency it has a finite gain, okay. Before this is a book which I follow and you can see why. There is the name somewhere is mine sitting there, so obviously I will support this book. This is a very famous book by Microelectronic Circuits by Cedra and Smith. I happen to share some 150 pages of that, so that is why my name appears. The typical, this is taken from page 34-35 of that book. There are 2 filters shown to you. The first one, which is RC network, R here and C here, is essentially a low pass filter, and the second one is capacitor here and resistor here, which is a standard high pass filter. And if you want to make any other filters, you just make a combination of these 2. It can be band pass or a band gap or a notch, whatever way you wish. The basic 2 transfer functions are good enough to create any kind of filters. Okay. However, these are passive filters. In real life, if time permitting this, I hope so, we will look into at least putting at least one LRC based filter using switch capacitors. So that possibly is the last part of this course. So we will implement a filter for that sake. Okay, so standard, if you see, I do not know whether you can read, but maybe I can see for one of them you can see the transfer function Ts for a low pass is some constant which is DC gain, as you can say, 1 plus S upon omega 0, where omega 0 is the pole value for this transfer function, and for high pass it will be S upon S plus omega 0, where omega 0 is again the pole for the high pass. If you write in T j omega form, S is equal to j omega, substitute there and you get this value. The magnitude response, which is essentially taking the magnitude of any complex function, a plus jb is under root a square plus b square, and its phase related to tan inverse b by a. Okay, so that's standard technique which we have been using for complex systems for last 3 years at least in IIT and maybe any years earlier. So we are interested in two response of any transfer function. One is called magnitude response and the other is the phase response, which is the angle associated with those poles or zeros. Okay. So that is given by tan inverse minus tan omega of omega 0. In this case it will be opposite of that, tan inverse omega 0 by omega, and we can say at omega is equal to 0, which we call DC. Okay, the gain is k, the other of course is 0, and the transmission at omega equal to infinity, the low pass gives 0 this and the high pass will give k. K is the DC value of that. We also define 3 dB frequencies. Essentially we say at that frequency the gain falls by 3 dB. Okay, that is the frequency we define. Essentially we will say the word later, I am going to use the Bode and what really Bode contributed. So that is, a few minutes we will come to it, and these Bode plots can be shown. So this transfer function is given in the book. These are standards, so can be looked into book, and these will be available to you afterwards anyway. If I plot its frequency response for the gain and the phase, this is called frequency response, and it is named Bode essentially for simple reason that Bode was the very old control system man. Okay, and he had a book of 1948 called Feedback Control Systems. So if you read that book, fantastic. So what Bode did, essentially if you plot a gain versus frequency, and this is log scale, normalized gain T dB by k, 20 log of that in dBs, and this is the frequency scale in tenths, that is decades. So 0.1, this ratio again normalized to omega 0, 0.1110. Okay, and you can now see from here, if I plot the gain versus frequency, as I increase the frequency, for certain frequency the gain remains constant and then it starts following as the denominator magnitude starts increasing, so obviously gain starts falling. Now this point, essentially if you see the transfer function, this actually at 1 the gain has already fallen to 3 dB beyond from the maximum, from its 0 dB, let us say. So essentially this point was called the pole point, where we can say the gain has started now falling below. Okay. However, what Bode said, extend it up vertically, put a horizontal line, and wherever this intersects he called it as a corner point or corner frequency. Okay. And then he started saying, okay, instead of using 3 dB points, use corners. Okay, because anyway you are not going to evaluate from this, what you are going to see, where is the frequency at which gain starts falling. So he actually made a simplified figure of this standard transfer function frequency response, and therefore they were called Bode plot. So nothing extraordinary, but something thought that time. So if you are asked Bode plot, don't draw 3 dB, then just draw this. Okay, that is what the Bode said. Okay, and at this point when omega is equal to omega 0, one says below that the gain will frequency higher than that frequency omega 0, then the gain will start follow, and if you see the function, this slope is 20 dB per decade of frequency change or 6 dB per octave. Octave means to the power 8 kinds. Okay, octodecimal, octal systems. Some people believe it is because Bode did 6 dB octave, so this book also retains that 6 dB per octave. Of late, being all decimal systems, we all have gone to decades, otherwise we will have to also change everywhere in form of 8. Okay. So this is essentially 20 dB or minus 20 dB per decade is the fall of the gain, and somewhere down here you can see at the frequency, which is much enough, it crosses some limit, but since it is minus there is no point of calling 0. But let us say this has some function K would have been not there, this would have been some positive dBs, and then it would have crossed a 0 dB line essentially when unity gain is observed, and below unity gain means there is no gain really, there is attenuation going on. So this point was very important in the case of normal transfer functions of an amplifier. What will be that point? Gain bandwidth point. Okay, so that's a very important point for us to know up to where gain is possible. If you get the T omega plots, phase of that, tan inverse omega by omega 0 minus because of the opposite signs. So one sees from here, if you see tan inverse 1 is 45 and tan inverse 0.1 is very close to 0, 1/10, okay, close to 0. And if you make tan inverse 10, which is close to infinite or much larger, it becomes closer to 90. So if you go your frequency from 0.1 to 1 to 10 times the omega 0, the phase goes from 0 to 45 to 90 minus, because minus tan inverse. So the slope down here therefore is called 45 degrees per decade. Okay, that is the slope with which this will actually go down. Since this was a low pass filter, the similar response can be shown for high pass. In this case the gain actually reaches maximum sometime at the, say, whatever the pole frequencies. The pole is on this side and the gain is falling on this side because it is a high pass filter. This was a low pass filter. Normally an amplifier response is closer to mixture of a high pass and a low pass. Initially it rises, then becomes constant and then falls. So this precedes this and you have a normal gain. But for op-amp this does not exist. Actually the gain even at 0 is finite, okay, because it can, that is the difference between normal amplifiers and an op-amp. At 0 frequency also DC can be amplified by an op-amp. Is that clear to you? And therefore there normally the response is exactly like this, it does not follow here. Okay. But for some reasons if you do some mischief putting some capacitor, some other resistors around, this can show a pass filter frequency even at the lower side. Okay. So it depends on the, like coupling capacitors at times forces you to get into a high frequency pass system, and therefore you may see even in op-amps which are called AC coupled op-amps, you may see a normal mid-band gain with fall on both sides. Okay. So this is something which, please remember, Bode plot and frequency response are no different. All that Bode did, of course there is a lot of theory which you read for the, it is a control system course, okay, and there all the worries are for only stability. This was only shown for non-stable, 100% stable system. We like to see in real life when we look for op-amp design, if there is a instability, how do you get rid of it and when the instability occurs. Okay. So we will like to see, we will see in case of small feedback system this, and we will show you that instability starts when something happens in a feedback, and in op-amp we want to avoid it because we want to make amplifier stable. Okay. So that is something we will see when we come to op-amp design, or at least stabilizing op-amp. Maybe initially we just look for frequency response and then we will figure out whether it was stable or not. If not, we will say okay, there are 3 more techniques which can make op-amp stable. Okay. Is that okay? So this is basic feature which all secondarites, at least I have taught. Okay. So let us look for a typical common source amplifier. Whatever is true for common source is true for common gate, common this. Basic equivalent circuit, once you draw, everything is identical for us. Okay. So example is only shown for a very trivial common source amplifier with a resistive load. If there is a current load, what will happen? RD parallel or 1 GM or R0 parallel, whatever it comes, corresponding loads will appear. As of now, RD represents load, whichever way you create. First thing we say, okay, if this is your this, and we right now neglect, there is a capacitance between gate and drain in a normal transistor which is called CGD, which is very important capacitance. Right now I have not shown it, but there will be capacitance here from the substrate, there will be capacitance to drain, capacitance to source, right now I am only interested to see input capacitance CGS. Okay. Also there is a output capacitance CDB. Let us say this is N channel and this is grounded, then there is a capacitance here which is CDB. Okay. Equivalent circuit of a MOS transistor we have done many days ago, so there is nothing great about. This CGS sometimes includes CGB, okay, because if the channel is not fully inverted, then edge of that may give you gate to bulk this capacitance. So essentially you can say CGS includes all of it, COX plus whatever it is, and this represents CGS. As far as circuit is goes, only the value matters, so I said it is CGS which may include CGB. Okay, so if that is so, I am interested in the output pole. First let us say, since this is no connection right now with this, CGD is not taken care, so no connection between input output except transformation because of the current source. Okay. And I assume right now R0 parallel RD, R0 is very high compared to RD and therefore it is RD. So if you see the pole which, if you look the gain V0 by this, the pole as an output frequency at which the gain will start falling is nothing but RD times CDB. So essentially this means if I calculate the time constants, I will be able to get the pole value. Is that correct? So basic idea behind all this is to evaluate corresponding time constants. However, if the equivalent circuit of amplifier also contains CGD, then some transformations are required because CGD will then be a part of input. Also you can see, if you see only input side, RSCGS is the only transfer function of this time constant available. So first input frequency related term is 1 upon RSCGS, output is related to this time constant. However, as I say, if there is a relation between this, there is a CGD available, then is that okay? 3 capacitances. Of course, there is a CSB also is possible, but that is lumped with CGS. So here is the equivalent circuit of a MOS transistor, amplifier, common source. I am applying a input signal through a series resistance of the source RS. This is my CGS, this is my CGD, this is my current source GMVGS. Please remember this is not Vn, this is GMVGS, this is R0, RD and CDB. We can always calculate VGS in terms of Vn by this simple divider rule, 1 upon CGSS upon 1 upon CGSS plus RS, and therefore I get Vn upon 1 plus RSCGS as the connection between Vn and VGS. So if I want to find V0 by Vn, I will replace VGS by this term and therefore I can always get the ratio of V0 by Vn. Okay, the assumption here is when I calculate this, this does not, because that impedance seen is much higher, so I neglect that. Okay. If you do not feel like doing this, solve all of it network. There is nothing, it will automatically come what I am trying to say. Okay, so these circuits we already solved n times, so I am not going to solve it again. I just have, using a Kirchhoff law, either in generally most cases is the nodal equations I solve. Okay. So if I use nodes and solve this circuit, there will be 2 equations and therefore always everything can be solved. So I get AVS is equal to V0 by Vns, which is minus GMRD 1 minus CGD, sorry, this is CGD by GM upon 1 plus RSCGS into 1 plus S times RDCGD. So if you compare this expression with the transfer functions, the first time I said S by omega z plus 1. So if you say when this term is equal to 1, that is S is equal to GM by CGD, the output goes 0, which essentially means you have a 0 of the transfer function. Okay, so the 0 is occurring at frequency of omega equal to Gm by CGD. Okay, and at that frequency the transfer function has a value of 0. However, if you look at this value, what is this value? If you leave all frequency terms, this minus GMRD is the, that means remove all capacitances from the circuit. This is the standard DC gain, not 0 frequency, DC gain, which is AV0, which is GMRD. Okay. So now you can see from the denominator you have 1 plus SRCGS, 1 plus SRDCGD. This denominator I expand. What is the purpose of doing all this now? I can see two poles here. Okay. When this becomes 1 minus 1 and this becomes, I have two poles anyway, I am seeing them. But I want to see whether they represent omega in and omega out, which I derived at least to great extent. If they do, then my solution becomes much easier to think. Then I will say, okay, look at only input, look at the output, I have two poles. Okay. To prove that I am okay, I will actually use expansion of this. You will get S square term, S term and constant, and from there we will figure it out which terms can be neglected, and therefore input and output poles can be represented right here. Okay, this is the trick which we want to use, and using that trick, what the new technique, not really new is a word maybe some of you, this technique is some 50-60-year-old, so new word is not true. This is given in Razali's book, so you can go back and look into Razali's book. D is equal to, I took some, this Gm which is here I have brought it down. Okay. So I get D is equal to Gm times 1 plus S of this into this. Okay. And if I connect the terms, I get something of this kind, and Gm Rd is minus AV0. So I get finally a term which is 1 plus S CGS 1 plus Gm Rd CGD into S. And what is being neglected here? We are trying to say S square terms are much smaller, okay, far off. Right now I kept everything, okay. Only thing afterwards when I expand, I left S square terms, and if I get this term then I get this 1 plus RS C in. If this is your C in, CGS plus 1 plus Gm Rd times CGD is C input, then the pole, this D is equal to 1 plus RS C in GS. If this is higher than 1, this is essentially a pole which is RSC in. Okay. So input pole is nothing but the series resistance or the resistance available in the input circuit and the net capacitance available. If CGD would not have been there, how much would have been CGA, the CN? CGS. So that was this with CGD. Why I brought this all expression here? This is giving me some idea that how to get transformation of CGD from the towards input side. Which method I should use that? What is the theorem we use? Miller's theorem. So this is the precursor to Miller's theorem. I figured it out that I can actually look into input side and see that the input pole is essentially same as what I would have got, except that now additional term of capacitance is coming because of CGD, and which is becoming very important and very large, because typically GMRDs will be more than 10 or 5 at least, if not more, and maybe 100 or 1000 sometimes. So in which case this term may start dominating this term. Is that clear? And therefore the input pole may become, that is the frequency becomes smaller and smaller as the gain is larger or the coupling is larger. Is that clear? What does that mean? If the frequency falls, means what does that mean? That the cutoff point is shifting to a lower frequency. So your standard DC gain is for a very short frequency range, and in normal amplifier what is the bandwidth definition? Up to which gain is constant. So essentially we are saying if this becomes the dominant pole, as we will see later, and if this omega in starts reducing because of this term or this term, then your bandwidth starts falling. When this increases, what does that mean? Gain increases, gain into bandwidth is the constant, you increase your gain and bandwidth goes down. So obvious reasons this is valid statement. Is that clear? So essentially we are worried about how much gain at what bandwidth. Okay, you cannot have, or if you want to beat little bit of that, what will you do? You cascade it, but the penalty you will pay for maybe some more power and some more hardware. Okay. Okay, so is that point clear? The point here is not very great, only I am trying to say I can always look at input poles itself to see the poles value, and I need not have to do all the except that to take care of feedback I have added this additional term. Okay, that took care. Now this all of you said suddenly, and here is the theorem which is very popular, all of us have been using for ages now. If I have a impedance Z between two nodes, a two port network, okay, where there is a gain function A which is Vy by Vx, this is very important term. A is Vy by Vx, is that clear to you? Then we can convert this to, this was a lateral, this I can break into two parallel Z1 and Z2, which still has the same potential Vx and Vy, provided we do equivalence of this, then Z1 is Z upon 1 minus A and Z2 is A upon 1 minus A into Z. Now this, please remember, if Z is capacitive, then correspondingly you must figure out 1 upon j omega C is the Z, please take it, otherwise do not go by random. Z is impedance, so 1 upon omega C will be the value of capacitive impedance. Okay. Okay. Is that okay? So this divider will be then actually will become multiplier for capacitance. That is why it is 1 plus gain times the C has increased. Is that point clear? 1 upon omega C is the impedance. Okay, so C becomes lower and therefore net capacitance actually increase. Okay, this is very important. Most of you know this working well and all that, but here is a problem which you should know all. A Miller theorem cannot be applied randomly, okay, and which is why an example is given. If I have a simple passive network shown here which is R1, R2, obviously Vy and Vx are not same. So Vy is nothing but R2 upon R1 plus R2 times Vx. So there is a gain, equivalently gain. But however, if I make a transformation, okay, by the two Z1, Z2 functions, on the one side I get R1 plus R2, which is as good as any input, this is fair enough value. But if you look at the output side, you get R2 parallel minus R2. You substitute there those values and you get R2 parallel minus R2, which means minus R2 by 2, R2 parallel R2, that means there is a negative resistance at the output impedance, which is not true, because in real life no passive device can create negative impedance. Is that correct? So now you do, don't worry, A upon 1 minus A, you substitute Vy by Vx, it will be 1 minus Vx by Vy, just substitute those values and you will get minus R2. Okay, I am not trying to add myself anything. Okay. So this essentially means that if I have a passive network, something like this, I cannot apply Miller's theorem. Is that correct? So what is that limitation Miller did not say but was imbibed by him? Unless there are two paths from input to output, Miller theorem is not valid. In this there is only one path. Is that clear? Is that word clear to you? All of you please remember, Miller's theorem is only and only valid if there are two paths from input to the output. Is that correct? Otherwise, like this, the Miller theorem will give you the output impedance absurdly value from that. Okay. This is a very, so if you have a normal amplifier, you have a feedback resistor here, the gain amplifier itself is one path. Is that correct? Through this input will go to the output. Currents are going, input will be transfer, current to voltage transformer or current to current. No. Amplifier, the signal goes from input to the output through amplifier only, na? GM VGS is transferring. Okay. So there are two paths, one through the amplifier and one through the feedback network, only and only then the Miller's theorem is valid. So please take it hurriedly, do not use transformation because वो T network दिखा उसको pi कर दिया और उल्टा pi कर दिया. Don't try something like this because that may lead to a absurd situations. Okay. Is that point clear to you? Everyone? Yes.
What is the meaning of two paths? I can always split R1 into two resistors.
No, but then at that node still same path. No. What you are saying is if I have this path, no, these are not two paths. They are same resistance splitting n paths here. They are not two paths. Here the phase between this and these are not same. There are two separate paths going on. Is that clear to you? Through A you are 180 degree out of phase you are going and one directly you are going, feed forward as the word goes, and therefore the Miller is possible. Is that clear? Because that in every case you say 1 upon 1 minus A upon 1 minus A has to be finite in this way. Otherwise that just divider output by input is not the gain function. Is that correct? And therefore Miller theorem is always valid only and only if it is an active device sitting there. So apply Miller only when there is an active device with feedback available to you. Apply Miller and you will not make any mistake in actual evaluations. Is that clear? This fact is known to many unknowingly, but now I thought you should be knowingly know that why we don't apply Millers elsewhere. Okay. Is that okay, all of you? Is this issue clear? Okay. Okay, since we are on the two-path system, here is something which I thought you should immediately connect to. This is nothing to do with the Miller, but the same concept I thought maybe I extend. If you see a normal transistor or amplifier shown here, and you have just now you said there is a capacitance CGD in our case or actual capacitance which you can pick, which is called CF feedback capacitance. But whenever if you have done a signal system course or normal signal theory or signal flow paths, we always assume there is no feed forward, there is only feedback. Okay. But in real life feed forward exists. Okay. If you have an input signal going from here, there is one way going to the output, the other is going through the transistors at the output. This will give you minus GM VGS, okay, because of the sign I chose, and this will give you directly what is the probable ICF, whatever it goes. Since this is a capacitive effect, that means the impedance is 1 upon omega C, so currents are functions of omegas. Okay. So it can happen that at this output node, if this current and this current are equal at a given frequency in magnitude, but since they differ in phase by 180, they may cancel. Okay. At that time the output will go to 0. Okay. So we say a 0 is essentially occurring because of the feed forward currents are matched by the transistor current which is out of phase at that frequency equal to magnitude of each. Okay. Then only you say there is no current and therefore the output DC AC output goes to 0. Is that clear? So this 0 word which people keep talking is essentially is using the same concept as we used in Miller's theorem. So I thought right now I should connect to you here that two paths is required to create a 0, otherwise there is no way function can become 0. Okay. So this has to be understood that why people, I mean it is not very big thing I am talking, but this is not understood by many that why 0 suddenly appear. Zeros occur because of, so here also there is an active device which is giving a phase 180 degree out of phase, this is giving 0 phase. If the difference of this magnitude becomes equal in at a given frequency, then only the net current will 0 and therefore net voltage will go to 0. This is a principle of 0. Okay. Is that okay? So please remember zeros are coming not out of nothing, they actually come because of the real situation which you see in amplifiers. Is that okay? All of you? Anyone? So returning to our problem of frequency response of a common source amplifier, a typical common source amplifier is here, equivalent circuit is shown here, the DC gain is GMRD, and using a Miller's theorem, now I can replace that CGD is 1 plus GMRD is the gain. So 1 plus GMRD, y minus become plus, 1 minus A is now 1 plus GMRD times CGD is reflected at the input in shunting the CGS, and A upon 1 minus A is close to 1, okay, GMRD upon 1 plus GMRD is 1. So I wrote only CGD parallel CDB. So the output, yes, equivalent, I just removed that. This CGD has two paths, one through GM VGS, one directly through CGD. Okay. GM VGS is appearing from the input, isn't it? That is the path. Okay, so if I now use Miller's theorem, I landed in this equivalent circuit, and then I have already said if I am not very fussy about exact values, the input pole and output pole can be directly seen at the output side and the input side. Okay, why? By finding the time constants. Is that clear? So what is the time constant on the input? RS time CGS plus CGD times 1 plus GMRD is the input omega, 1 upon that. Similarly, RD into parallel combination of CGD and CDB, that is sum, CGD plus CDB is the output pole. Many cases this CD may be very dominant term. Why? Raj? Many a time those CDB value may not be more than half a puff or less, but that value may be very strong because of something else. What? If there is external capacitance, that is you are driving next system which has a large input capacitance, this will appear here. So that is why when you calculate poles, the output of input of the next stage must be used as the output for you, because in real life this is what it is going to see. Is that correct? Is that point clear? So at that time if CL is very large, the output pole become very small frequency and that may become dominant. Okay. If the CL is smaller or comparable to these values, then probably this may still dominate. Okay. But in many cases if CLs are actually put, that may become dominant. So do not go by my statement every time that this will be dominant. You check it, which one is smaller is the dominant. Is that equivalent circuit okay, all of you? These are trivials, you have already done in second year. I am just trying to repeat because I thought this method which is relatively standard, I am now going to compare with the new 50 साल पुराना old new technique, zero time constant technique, which many of you have learned. If you have done my second year analog course, I taught them there. But there, if I recollect well, I did not teach what is the other method of, you can always calculate dominant pole, and I did not show them how to calculate non-dominant pole. Today I will show you, I can also evaluate non-dominant poles. Okay. Is that okay? Figures are okay, everyone? Okay, is that okay? Will be?
Sir, you are telling CL, but it should be CE of other amplifier.
Because the next device I do not know, if it shows me what is that I am driving and if no load is known. Normally in all circuits, you know you are connecting to some stage. So you roughly know the input capacitance of that stage. Okay. In digital what do we say? At least one Cox it should drive. Okay, and to safety we put at least 4 Cox drive. Okay, so we are guaranteed that the next delay is not worse than this what we have calculated. Okay, यहाँ भी कुछ assume कर सकते हैं. Single के लिए ये ठीक है. Method is same. Okay. Okay. Using our technique as I suggested, I can find omega in and omega out, which is RS CGS 1 plus GMRD times CGD input pole, and output is 1 upon RD. Please remember this is radians expressed in radians per second, and actually if you want frequency you divide by 2 pi and you only get hertz. So right now omega and frequencies are talked in same vein, but they are not. 2 pi f is omega, please remember, unless you divide by 2 pi this is not hertz. Okay. Maybe in example which I saw I will show you hertz. Okay. So typical transfer function then can be written, and right now I have given up that 0 because I am not very keen about that 0, but if you wish we can do that as well, no problems. AVS is AV0, upon 1, because this I am using it, which I am going to be using 0 value time constant method, and the actual method is what that person was asking. You have a network, solve 2 nodes, get exactly whatever you wish, no terms are neglected, no terms are, you are not missing anything, okay, कौन बड़ा कौन छोटा सोचो मत, सब ठीक है. But if you want to see approximately equal, then tricks have to be followed. Otherwise, as I say, if everyone does it, Kirchhoff law, there is no mistake, because SPICE doesn't do mistakes, simply you guys only solve that network. Okay. So SPICE results and our results, but then why are we doing this? Because even to tell SPICE what W bar I should start, I should roughly get values now this much bandwidth. Okay. So first order guess. Okay. Otherwise what happens? Step by step 1 million years के बाद output. Okay. Okay. So this is typically what the transfer function looks like. Okay, the statement I was making, if you want to solve by Kirchhoff law, a huge expressions like this will appear. This may gives you 2 poles omega p1, इसको s1 plus कैसे करते हैं, partial fraction से s plus 1 plus s plus 2 जो भी है उसको expand करो, equivalent निकालो और ये निकाल सकते हो. So इसमें ये 2 पोल्स निकाले, तो ये RS1 plus GM CGD, RS CGS plus RD CGD plus CDB, omega put is 1 upon ये पूरा term into 1 upon RS RD, this is using Kirchhoff law. Okay, so someone, now you can verify what has been done in the 2 cases, under what conditions. This is same as what we did, and this is close to something which we have done. So conditions लगा सकते हैं. यदि ये टर्म मैंने छोड़ दिया तो पहला वाला टर्म आ जाएगा. If RD CGD plus CDB is smaller, okay, then this terms, then omega in is same as omega p1. Is that okay? I'll just look at this term. If I neglect this, this is what my pole was. Okay. So थोड़ा सा overestimate हुआ है. This is very trivial, just as I say solve 2 node situation, एक में करंट ऐसा, एक में करंट ऐसा, तो इक्वेशंस बन जाएंगे और सब कुछ सॉल्व हो जाएगा. Which one you are talking? Oh, C equivalent, oh sorry, I should have written somewhere. C equivalent is combination of all C's, CGS CDB, CGS CGD, CDB, whatever 3 capacitance का 2 का combination लो, that is equivalent. Okay, maybe I'll write, I may not. CGS CGD plus CGS CDB plus CGD CDB. ठीक है? हाँ? Capacitance, these are all radians per second. ओमेगा है, यदि 2 पाई से डिवाइड करो तो हर्ट्ज हो जाएगा. Oh, okay, okay. You don't call it dimension, it is square per square of farad square. This is a product. Yeah, this is all some representation. Okay. You are right. This doesn't give units. This only says C. Okay. You can see from here, if no, she is right. 2 resistances are there, so I need 2 capacitances. These are 2 capacitances. Is that clear to you? To make a time constants, I need RSC, RDC. These are CCs. So it is C square I could have written, but I said anyway I am not using it, so I used only C. Okay. Is that, it's only representation, please don't go over it. The basic idea you can see, if there are 2 resistances and S square term appear, obviously there has to be 2 capacitances there. Okay. Okay. The condition which I wrote, if RD CGD CDB is smaller than this term and then CGS is larger than this term, this omega p1 and omega p2 reduces to the same values which we derived with using Miller. Okay. Now in most cases and not all cases, this may be valid. Okay. And therefore in many cases using Miller, the values are good enough, okay, good enough. Like let us say if it is a cutoff is 4 megahertz, we are overestimating to 4.5 megahertz, okay, okay. That is all that will happen if you do not use accuracy, okay. But otherwise anyway start point देना है तो 4 क्या और 4.5 क्या. Now I am not saying that we should not, if you want very accurately expression है ना, I mean no one is stopping you substituting everything there, okay, do substitute, get 3.63489 whatever decimal hertz, okay, your choice. No, I am not making fun, but this is an issue which one has to understand in engineering up to what accuracy one should look at, okay. The reason why we do not go too much on this is in our assumption right now, when I actually put this design on a chip, there are other parasitic capacitances available to me, even parasitic resistances will be there, which right now I do not know, okay. So anyway मैं estimate ही किया है, तो फिर थोड़ा और estimate कर लें, that is the idea. In real life what we will do is we will actually do this simulation, find says lay it out as we shall show you, then extract from the layout the circuit which then takes care of all the additional parasitics which layout will give, and then you will find the first values which you started with did not match with the you got back, then pick till you get as good as match, okay. That is the design. कितने बार ऐसा ट्रिक करना अच्छा रहेगा, एक बार, पहले बार में आया तो you must then correctly find which will give me correct. If you do second turn around, you lost money. If you take third around, you will be thrown out. Okay. So, is that clear? Under certain conditions, the Miller theorem is relatively okay values it will give, and you can still start with these designs as a guessworks. Okay. Now, one of the things which all Miller theorem assumes, and which is what the other theorems will also, it assumes as if there is a dominant pole. Okay. We started with this assumption. If the two poles are close by, the Miller theorem may create lot of problems. Okay. So selectivity will become very difficult, and this theorem should not be then applied. Okay. But in most of the amplifiers which we use for a variety of other specification, there will be a dominant pole and the next pole will be away, far away, and 0 may be even further away, okay. And therefore this calculation of dominant pole is not that bad as one thinks, though reality you can always get the accurate poles, okay. Now since we have figured out in every such calculation RC we were looking, the frequency is calculated based on time constant. So we said why do all this then solve the network also, why not we use little different technique to get the time constant themselves, okay. If you see your expression little carefully, एक टाइम कांस्टेंट यहाँ पर है, एक टाइम कांस्टेंट यहाँ पर है, एक टाइम कांस्टेंट यहाँ पर है, इसको यदि सेपरेट किया जाए तो दिस विल बिकम RS, ओके नहीं इसमें इसको इसके साथ जोड़ा जाए तो दिस CGD और एक CDG RD प्लस दिस इंटू CGD एक टाइम कांस्टेंट है, RS इंटू दिस प्लस दिस इज अनदर टाइम कांस्टेंट है. सो all that we are seeing is there is a sum of time constant is all that is you are getting through all that expressions, okay. So यदि मैं individually या निकाली लूँ then I don't have to do all that analysis, I just figure out those three and add, okay. This is essentially the technique which is very popular in designers. It is called, बाकी कुछ मत लिखो, last line लिखो, last दो line लिखो. This suggests a simple technique of evaluation of poles using a technique called zero value time constant, also popularly known as open circuit time constant. This always figures out the dominant pole. Is that clear? Zero value time constant technique always evaluates dominant pole, okay. The other term which it appears, okay, is essentially, we will call it short circuit time constant analysis, we will show it later, and that will give you non-dominant poles. Open circuit time constant analysis gives you dominant pole. Short circuit time constant analysis will give you non-dominant poles. Okay. मैं लास्ट में फिर से एक बोलूँगा. We are assuming the zero is far away from the pole frequencies. What does that mean? They do not contribute to the till you reach GB. Okay, so they have no chance of coming earlier than GB. Zero frequency is 10 to 100 times of the GB. Okay, so they do not bother us in any sense. Okay, okay, is that, you don't have to write this, I already said. Basically I figured out that if you see poles, time constant है ना, so individually why not I calculate. Okay, and then how do I calculate is the technique which is shown here. Okay. For each time constants, take whichever capacitor you are looking into, for which time constant you want, leave that capacitor, but all other capacitors, they should be open circuited or impedance should be open. They should be open circuited means actually the impedance is infinite as if there, so just open. There is other technique which I will show you in which actually capacitors are shorted, that is impedance is one like that. Actually C is shorted, C is made infinity for all capacitors are now as if not existing. Okay, so and short all independent voltage sources. जब भी कोई R निकालने का तो what is the technique? Apply source, find the current, short सबको सब, same technique, nothing great. Open all current sources, independent one, and short all. So GM VGS is not independent source, huh? It is dependent on VGS, so don't short it or open it. Okay. Now we want to calculate a resistance R1 corresponding to the chosen capacitor C1 and then find out the time constant which is R1 C1. जो भी C1 choice किया है, how much resistance it sees in the circuit using this, that I will call it R1, and the time constant associated then I will call it R1 C1. Repeat this for all capacitors one by one. C1 हो, फिर C2 करो, फिर C3 करो, Cn करो, जितने भी हो सबका करो, and then add all time constants. ये थोड़ा सा ये गलत छप गया था इसलिए this essentially 1 upon sigma Tj and not sigma of 1 upon Tj, because that is harmonic mean, that will get into your problems. I repeat, this is not sigma of 1 upon Tj, it is 1 upon sigma of Tj. Is that clear? They are two different. The other one will give you harmonic means and that will be absurd then. That is sum all t taus and 1 upon tau is the net tau you get, okay, which is essentially your first time constant related omega minus 3 dB point, the first corner is called dominant pole. Okay. एक calculate करके दिखाते हैं आपको अभी. This is the technique, zero value. For the circuit of common source amplifier, we obtain minus 3 dB point using ZVTC technique. ये आपका equivalent circuit है, okay, और अभी मैं CDB को छोड़ देता हूँ, okay, even मैं CGD को भी अभी हटाने वाला हूँ, क्या मुझे I don't want them to be there. Now I want to see, seeing from CGS, what is the resistance it is seeing. If this is not there, this is not there, ये हटा दिया, okay, then I see how much is the resistance is seen by CGS, only RS, only resistance is seeing is RS. So RCGS name if I get, then RCGS is nothing but RS. So the first time constant as seen by CGS is RS times CGS. तो पहला कपार वो एक्सप्रेशन देखो उसमें एक RS CGS टर्म है वो आ गए आपकी. Okay. Is that one clear? The first in the denominator see one of the term is RS CGS that has now appeared. You open this capacitances and at this CGS what is the resistance seen by it. It does not see anything here, there is no connection here. So all that it sees is and short input independent source. Okay, इसीलिए ये RS इसके across आ गया है ना. So RS is seen by CGS. So time constant associated is RCGS or RS times CGS. Is that okay, everyone? Now what else I should do? Which capacitance I should do now? CGD. CDP को ओपन रखेंगे और CGS को भी ओपन कर देंगे. This is called zero value, that's why it is open circuited. Now I want to see CGD के अक्रॉस क्या है. तो वहाँ एक करंट सोर्स लगाया और उसके अक्रॉस जो वोल्टेज ड्रॉप है V by II is the resistance. I short the source, I open CDB and I open CGS. Is that correct? So this is the circuit I get. This is like using a Kirchhoff law. I solve this. This is just solving again Kirchhoff law, but follow circuit. I open CGS, I open CDB, I put a current source test current and drop across that is my V test or VGD. Ratio of that is the resistance seen by this capacitance. So if I solve this, I get RS plus RD plus GM RS RD. So that is my resistance seen by CGD. So what will be time constant? RCGD times CGD is the second time constant. Now start looking in this expression. इसमें यदि RS RD common है 1 plus GM RD term आ रहा है. 1 plus GM RD times RS ये term आ रहा है उसमें, आपके expression में भी है. I open CGS, I open CDB and across CGD I want to find the resistance as seen by this. How to get the resistance? Any point between 2 points I apply either voltage or current source and find the ratio there. Okay, so I applied I test. Okay, I later on call it test, so I will also call test. Okay, so I apply current source I test and measure a voltage across these 2 points. The ratio of the two is V by I is the resistance seen by this. Once I put this, then solving network should be simple. So RCGD is RS plus RD. Okay, please quickly. So tau 2 is RCGD times CGD. So this is the expression for this. Then the step 3. Which is the step 3? Open VGS, CGS, open CGD and start looking from the CDB side what is the resistance seen. So you can see since VGS is 0, you have shorted this current source is not existing. So resistance seen by CDB is only RD. Is that correct? So it is tau 3 is RD CDB. So 3 time constant आपको 3 capacitance के मिल गए. Please remember every capacitance will give a pole. Is that correct? So 3 time constant should be available if you have 3 capacitors. So tau 3 dB is tau 1 plus tau 2 plus not 1 upon tau 1 plus 1 upon tau 2. It matters hell of it. So sum total किया. Which pole I am going to get through this method? Dominant pole. Okay. वो जो आपने ओमेगा P1 देखा है ना, वो आना चाहिए इसके बाद. आ ही रहा है, वैसे दिख ही रहा है वो. ये प्रूव करने के लिए इतना सब किया मैंने कि ये मेथड ही ठीक है. क्विकली कर सकते हो और थोड़े दिन में आपको यदि CGS CDB के वैल्यू पता लग गए ना तो आप बाकी इसको भी छोड़ सकते हो. क्या ये ठीक है, ये इतना ही हो, ये इसका कट ऑफ है. दैट इज व्हाट डिजाइनर्स डू. सो फर्स्ट ऑर्डर क्विक थिंकिंग होना चाहिए बिकॉज दे विल स्पेसिफाई यू बैंडविड्थ. मोस्ट amplifier designs or most analog people will specify you bandwidth because that is up to which it should work. So that number should immediately be seen what is the up to which I have to do, and that is very crucial for our analysis. Is that okay? So F3 dB 2 pi F3 dB is this expression, and you can see this expression is almost same as the expression we derived earlier for omega P1 using Miller's theorem. So essentially zero value theorems are representing Miller's technique. Is that clear? And this pole is dominant pole. Now there is other poles if you want this full stop is के बाद. For non-dominant pole too we must know another technique which then I will get this. Okay. That method is first method का नाम actually दूसरा क्या था open circuit time constant technique. उसका उल्टा है शॉर्ट सर्किट. अब कैपेसिटर को जहाँ ओपन कर रहे थे ना उसको एक्चुअली शॉर्ट ही करेंगे. So instead of telling you the technique, I have chosen maybe 5 मिनट में हो जाएगा. I give an actual example which will get dominant and non-dominant poles. Okay. अब जो मैंने वैल्यूज कैलकुलेट किए हैं वो मत पूछो और फाइनल वैल्यू लिख लो ताकि सॉल्व करना. मैं अभी आपको सिर्फ एक्सप्रेशंस का डेटा दिखा देता हूँ. okay. मैंने सॉल्व किया है आप फाइनल वैल्यू लिख लो. Okay, here is an example. I want to find the dominant and non-dominant pole of this amplifier. These values which I have changed from my value, you note down this and solve the same example with these new values and inform me next time at least one of you what are those values. There I am doing a separate data but I asked you to solve RS 10K, RL 10K, CGS 1 puff, CGD 20 puff, GM is 3 milliamp per volt. ये डेटा आपको कैलकुलेट करना है. I am going to use ZVTC technique to find dominant pole and short circuit time constant technique to find the non-dominant. Right now I have not used CDB, we can use it to simplify. I have just in most cases CDB can always be, this you have to solve anyway. So you note down this. This is a old common source amplifier equivalent circuit, CDB is neglected as of now. Nothing very great. Okay. However, this technique is given in Gray and Meyer's book. Those who wish to know it, Gray, Meyer, new names, 2 more names have come now, Hertz and something. Here is the data. RS is 1K, RD is 5K, IDS is 1 milliamp, beta dash is so much, rather beta dash into W by L is 100 milliamp per volt square, CGD is 0.5 puff, CDB, अच्छा CGB भी 0 है और CDB तो है ही नहीं, ओपन है. So I calculate GM to beta IDS. Okay. अभी तक कोई चेंज नहीं हुआ, करंट सोर्स बायसिंग इक्विवेलेंट मिरर से दिया है. So GM is 2 into 100 10 to power minus 3 into 10 to power minus 3 किया तो 14.1 milliamp per volt. Now we first calculate the things using Miller's theorem. मिलर ने बोला है ये पोल है इसका, ये ओमेगा P1 है 1 plus GMRD RJ CGD. सो इन सब की वैल्यूज मैंने एक एक मेरी मेथड आपको बताता हूँ. मैं पार्ट बाय पार्ट वैल्यू कैलकुलेट कर लेता हूँ, यानी मिस्टेक होने का चांस थोड़ा कम हो. इसकी वैल्यू होती है बट दिस इज व्हाट. सो यू डोंट फॉलो एनीथिंग हियर, you write down this and I will give the final answer. Time is running out. Okay. I repeat omega P1, this you should write data, GM maybe you can write, I have calculated. The pole is, dominant pole is 1 plus GM RD RS CGD, RS CGS plus RD CGD. This is by Miller's theorem. Substitute all of it as given there by writing those data which I have calculated. So the dominant poles appears at 3.68 megahertz. The second pole from the Miller's theorem is RDCGD. So I calculate that to be 63.6 megahertz. Okay. Miller ka, these are Miller theorem, and what is the technique I am comparing it with? Zero value and short circuit. ये short circuit से निकालेंगे और ये ZVTC से करेंगे. If I use ZVTC, the tau 1 is RS CGS, अभी कैलकुलेट दिखाया ना फंक्शन, उसको यदि रखा तो it is 5 10 to power minus 9. Tau 2 is RS plus RD CGD plus GM RS RD CGD, इसीलिए वो एक्सप्रेशंस कैलकुलेट करके रखे हुए थे ना, वो इजी सब्स्टिट्यूशन के लिए. So tau 2 will become then 3 into 10 to power minus 9 plus 35.25 into 10 to the power minus 9. So the dominant pole is 1 upon tau 1 plus tau 2. This comes 3.68, same, because ये term same है वहाँ पर, okay? इसलिए same आया. Okay? नहीं होगा तो थोड़ा चेंज होगा, नहीं क्योंकि इसमें सिंप्लीफाई मिलर को भी सिंप्लीफाई रखा हुआ है, इक्विवेलेंट छोड़े ना कुछ टर्म वो रखोगे तो थोड़ा अंतर आ जाए। ओके, इज दैट ओके? In our Miller expression we have neglected some term to get smaller version, but if you use exact one, this value will be slightly different from the one which I will get from ZVTC, I mean I got from this. Now what is the next pole I want? The non-dominant. This is the dominant, lower frequency. Survi ji note down हो गया, FP1 is 3.68 megahertz, tau 1 tau 2 पहले ही कैलकुलेट हो चुके हैं, वो सब्सटीट्यूट किए जा रहे हैं. The next technique is for the capacitance you are really looking for, okay, let's say I want to find resistance seen by CGD. So बाकी सब capacitance को physically short करो, यहाँ short कर दो, यहाँ अभी रखा ही नहीं था तो इसलिए इधर का कोई सवाल नहीं आया. So as soon as I short this, ये सब तो गया, वैसे भी Vin shorted है, RS short means ये भी short हो गया. So CGD is only seeing this, since there is no voltage here, no current source here, so CGD is only seeing RD. So the RCGD, that is resistance seen by CGD, is RD. So tau CGD is RD CGD, which is 2.5 to the power minus 9. Is that clear? All other capacitors physically short them, and then from the capacitance you want to see how much resistance it sees. That is its equivalent resistor. What is the next capacitance I have? CGS. So what should I short? CGD. Okay. But now VGS is not 0. Is that clear? Because CGS is have a drop now. So GM VGS. However, you can see from here, this is VGS and this is also VGS. एक करंट सोर्स के अक्रॉस यदि सेम वोल्टेज है, जीएम वीजीएस का वोल्टेज ड्रॉप, तो क्या मीनिंग है? इक्विवेलेंट रेजिस्टर्स ऑफ 1 अपॉन जीएम. सो यू कैन सी आरएस पैरेलल आरडी पैरेलल 1 अपॉन जीएम is the resistance seen by CGS. So RCGS कितना है? Please, now we are waiting, finishing. RCGS is RS parallel 1 upon GM parallel RD. Okay. And if I substitute all these values for tau CGS, I get 0.325 into 10 to the power minus 9, okay, and therefore short circuit time constant is sum of this plus CGD, which gives me 2.825 into 10 to the power minus 9. So if omega non-dominant is omega P2 1 upon this, which gives me a value of 56.3 megahertz. How much was the by Miller? 63 point something. So we are slightly, by this technique, we are slightly lowered this pole. But you can still see this is 63 or 60, and what is the dominant pole? 3 megahertz. So we are really far away from each other, so the validity is as good as long as these are separated. So यदि एक पॉइंट पर दो पोल आए तो ये टेक्निक फेल हो सकता है, स्क्वायर टर्म वहीं पर है, तो दिस में नॉट बी. देन यू मस्ट सॉल्व किरचॉफ लॉ. इफ एनीथिंग इज वरीइंग सम, डू देयर. इज दैट ओके? So I can calculate the dominant pole, I can calculate also the non-dominant pole. Third pole अभी ऐसे भी कर सकते हैं, पर second के बाद we are not, because anyway the 40 dB down शुरू हो गया, तो we are not worried about that. Okay. Both these techniques, few comments and few limitation comments. These do not lead to finding zeros. First thing you must see, I have neglected in my, there is no way I am calculating zeros. What is the assumption in that case? Zero is far away from poles. Okay. So no worries. It is accurate enough, there exists, अभी जो मैं बोला फिर से वही लिखा हुआ है. These techniques are good enough if there exists a dominant pole separated by larger frequency difference from the non-dominant pole. As long as ये दूर है, ये technique valid है. In most amplifiers, luckily for us, in most analog system, this condition is normally met. But exam में मैं जानबूझ के उल्टा कर सकता है. That's another issue. In this technique, remove another catchword, this is very important for actual designers. in all the actual circuit there will be a coupling capacitor to separate DC and AC. These values are microfarads. Okay. So do not use them because at normal frequency of any higher there will be anyway shorts. So do not use those capacitances in any ZVTC or open short circuit calculation. Just short them out. They are not there. Is that correct? So in this technique, remove coupling capacitors, that means short them by providing shorts at higher frequencies. So this is a catchword, otherwise actual network में वो C दिखेगा उसके पीछे भी लग जाओगे आप, okay? क्योंकि वो तो सबसे पहले वो दिखाएंगे आपको पोल. Okay, so he said to leave that whenever you calculate the bandwidth for any amplifiers. Omega P1 is called, or P1 is called the bandwidth of the amplifier. Is that correct? Is this technique clear? So please remember, these are the designer's way of looking the things. Kirchhoff law is always true for all circuit people, irrespective whether you design or you don't. Okay. Is that okay? So on Friday we'll start with op amps.